So let's go ahead and take a look at example 1. So really what we're trying to do is look for some key elements of this graph, some kind of defining characteristics like the asymptotes in x-intercepts, or if there's like holes or things like that. And if once we find those things, then we can kind of depend on our graphing calculator to kind of give us a little more information to get a respectable sketch. So the first thing that I always look for are the vertical asymptotes. And as we've seen in our previous examples, if we're going to have vertical asymptotes, they are going to come from some value that makes the denominator 0. And so when I look at this denominator, I can tell that there is going to be an undefined spot when x equals 2. And I know that this is not a hole, as we discussed earlier, because I can see that that factor x minus 2 does not cancel or have the same factor in the numerator that would cancel out. So it doesn't create a hole, it actually creates a line of discontinuity, which is an asymptote. So I know over here on my graph at 2, I have a vertical line here that's going to split this graph. Now the numerator also tells us something about the graph. It actually is going to tell us the x-intercepts. So I can see that this graph is going to cross the x-axis when x is -1, because that makes the numerator equal to 0. So I'm going to go ahead and put that on the graph. At -1, this graph's going to cross the x-axis. Now another really important feature is whether this graph has a horizontal asymptote or not. And if it doesn't, it could possibly have what's called a slant asymptote. So how we would be able to tell if this had a horizontal asymptote to begin with is we're going to look at this table right up top here, and we're going to go take a look at this, and it tells us how to compare the numerator and the denominator to see if there actually is a horizontal asymptote. So when we look at this table, we have to have a little context. When they say p of x, they actually mean numerator. So p of x means the numerator, and q of x means the denominator. And in this table, they compare the degrees of the numerator and the denominator. And so what we mean by degree is it means the highest power on the exponent. And so if we have a degree of a numerator, p of x, in other words, if the numerator is less than the degree of the denominator, then we're going to have a horizontal asymptote at y equals 0, which is really the x-axis, right? So there again, that's if I see a higher power on the bottom, say like I have an x squared on the bottom, but then I only have an x on the top, that means there's going to be a horizontal asymptote at x equals 0. I'm sorry, y equals 0. Now if instead the degree of the numerator is the same as the degree of the denominator, then you're going to have that horizontal asymptote at a line that is determined, horizontal line determined by dividing the leading coefficient of the numerator by the leading coefficient of the denominator. So that basically just means that it's going to be a horizontal asymptote that is either shifted up or down from the x-axis. Now there's one final scenario, and that is if the numerator's degree is actually greater than the denominator's degree. And if that happens, that actually means that there is no horizontal asymptote, but it doesn't mean there's not something else besides the vertical asymptote that we would get from looking at the denominator. It means that it's possible that there is a slant asymptote. And we're going to take a look at when there's a slant asymptote. It actually happens when the numerator is 1 degree more than the degree of the denominator. And we'll talk about, as soon as we come across one of those, we'll talk about how to find that slant asymptote. So it's basically going to be an equation for some sort of oblique line that will be in y equals mx plus b form, and it will be a slanted line that divides the graph similarly to how the vertical and horizontal asymptotes do. So looking at our particular graph we're on right now, we can compare the degree of the numerator and denominator, and you can see that they're the same. See how they're both x to the first power? And that means we're going to use the scenario in the middle here, that when they're equal to each other. And so what that means is I'm going to have a horizontal asymptote at the equation y equals, well, the coefficient of the numerator is 1 and the coefficient of the denominator is 1 for the leading coefficient. So that's 1 over 1, which equals 1. So this is going to be at y equals 1, which is going to be right here. And so now I know my vertical asymptote is at x equals 2. My horizontal asymptote is at y equals 1. The graph's going to cross the x-axis at -1. And so from here, I'm going to go ahead and take a look at the graphing calculator, although I can kind of already tell basically what this is going to look like. It's going to look something like this over here, because of course it's got to follow those asymptotes and it's got to cross through that x-axis there at -1. But just to make sure what it looks like on the other side, I'm going to go ahead and look at this graph, and here's what it looked like when I typed it in my calculator. So it was just really as I anticipated, that it looks basically like one of those hyperbolas that is shifted 2 units to the right and 1 unit up. And had I put my original function into using long division into that format, I could have seen that. But so I'm just going to go ahead and sketch the other branch right over here, and that gives us a pretty good representation of that function f of x. Let's go ahead and turn the page. We'll look at some more examples. Okay, so our new function is x squared plus x minus 2 all over x plus 3. So again, if we're going to put this in our graphing calculator, it would be a good idea to put it in from the start like this, just because less parentheses, just really making sure I distinguish the numerator from the denominator. Or if you have one of the newer updated graphing calculators, you can use a stacked fraction to just type those in the numerator and denominator. But I know that I have to find those key features. And the first one I always think to look at is the denominator, which tells me the vertical asymptotes or whether there's holes. And so just to be safe that maybe there's not like a hole here, I want to make sure I look to see if there's a factor of x plus 3 in the numerator. So I'm going to go ahead and take that numerator and I'm going to factor it down. And when I write it in factored form, I know I've got 2 binomials. We'll start with x. They're going to end with numbers that multiply to -2 that add to +1, which is +2 and -1. And so, yep, I can see that there's not a common factor in the numerator, so I can depend on that denominator being a vertical asymptote. And so I know that x equals -3, I'm going to have a vertical asymptote. So I'm going to go ahead and put that on my graph at -3. And I'm going to label that x equals -3 right here. And I'm going to look at that numerator. So remember, the numerator is going to tell me my x-intercepts. So my x-intercepts are going to be what makes that numerator equal to 0. And there's 2 places where that happens. It happens at when x is -2, as well as at 1. So it's going to cross 2 places. Once at -2, I'm going to go ahead and put a point there where it's going to cross at -2 and also at 1. And then I'm going to go on and take a look at the degree of the numerator and denominator and compare to find my horizontal asymptote, if there is one. So comparing the degree, this is the highest power of the numerator and the highest power of the denominator. The higher power is on the top. So if we were to look at that table over on that other page here, we can see that that scenario that we have there with the higher power on the top is down here, right? It's this one. And so what it's saying to me is that there is no horizontal asymptote. So I know that horizontally there is no break in this graph. So horizontal asymptote, there is none. I'm just going to put none there. But remember, we talked about this thing called the slant asymptote. And we said if the degree is 1 higher on the top than on the bottom, and that is the case here, because the degree is 2 on the top and 1 on the bottom, that there's a slant asymptote that is the quotient of those 2, of the numerator and denominator. So if I take and use long division and divide that numerator by this denominator, I'm just going to go ahead and do that here. So I'm going to divide x plus 3 by, or x squared, sorry, plus x minus 2 by x plus 3. And the resulting quotient will be an equation in slope-intercept form for the slant line. So when I go to do long division, I'm just going to see how many times does x go into x squared. Well, that goes in there x times. X times x plus 3 is what I'm going to subtract, so that's x squared plus 3. I'm going to subtract that from above, so I'm going to change this to addition of the opposite, and these will cancel. When I take x and add negative 3x, I get negative 2x. I'm going to bring down the negative 2, and then I'm going to divide again, so now I'm going to see how many times does x go into negative 2x, and it goes in there minus 2 times. Negative 2 times x plus 3, I'm going to then subtract that, and that's negative 2x minus 6, which when I change that to addition of the opposite, that's going to leave me with a remainder of positive 4. So that's the remainder, but the part that's really important for me right now to get that slant asymptote is the x minus 2, or the quotient. So it's telling me that I have a slant asymptote, an SA in other words, at the equation in slope intercept form of y equals x minus 2. And I know that that means that the slope must be 1 because there's no number in front of the x, and that negative 2 is the y-intercept. So I can go ahead and put that on here as a slant asymptote by plotting the y-intercept at negative 2 using a slope of 1 to rise 1 and run 1. Kind of generate some points. Rise 1, run 1. Rise 1, run 1. I could also go down 1 and left 1, down 1 and left 1, because that's still producing a positive slope. And then when I go to connect those, and again for asymptotes I always use dashed lines, then that's going to look like that. So I have this, still have the coordinate plane really divided up into 4 sections, just like I did with hyperbolas. But this time I maybe either are going to be graphing in here, or maybe I'm going to be graphing out here and have my 2 branches. And so to know for sure, I'm going to, well, and I'm pretty sure it's going to be in here, and that's because you can see these x-intercepts are in that region in there. But in order to know for sure, I'm going to go ahead and take a look at the graph. So here's what I found when I put this in my calculator. And that really makes just complete sense when you look at that, given the framework that I have set up, because you can see that this portion right here is going to fit right nicely right in here. And I can see it's going to cross right through those x-intercepts that I established and then follow along those asymptotes on either side, one being the slanted one and one being the vertical. And then I've got this other branch right down here. And if I wanted to be really accurate and specific, I could find some specific points down in there by looking at the table. But this looks like a pretty good representation of that graph, just given those key attributes: the vertical asymptote, the x-intercepts, the fact that there was no horizontal asymptote, and the fact that there was a slant asymptote at y equals x minus 2. We were able to get that framework, and then with the help of our graphing calculator, get the rest of the sketch. Let's go ahead and take a look at one more. Oops, and by the way, they did ask me to establish the domain as well. So just remember your domain. You want to make sure you don't include any values of x that would make the denominator 0. So the easiest way to write that is in set notation. And I would just say x such that x cannot equal negative 3. And that's my excluded value. Now the range would be quite a bit harder to establish. We'd have to really know exactly what that gap is in between those 2 branches. And so for now, we're just going to go ahead and focus on finding the domain. Now let's go ahead and take a look at example 3. So again, we want to approach this the same way. We're going to take a look at the numerator and denominator, see what information we can get from them. But the denominator, we want to make sure we put into factored form to begin with. So I'm going to factor that x squared plus 3x minus 4. So that would be x minus 1 and x plus 4. Pretty close. It almost canceled with the numerator, but I had an x minus 1 instead of an x plus 1. So that means there's no hole in this graph. And so I know, again, if I want to graph this in the calculator, either go back to the original and parentheses the numerator and denominator, or just go ahead and put it in like this with your division sign in between if you want to see what this is going to look like. But taking a look at that denominator, that's going to tell me vertical asymptotes. In this case, I have two of them. I know that the vertical asymptotes are going to be when x is 1 and when x is -4. So this is going to have two breaks side to side. There's one at -4 here, and then again that equation is x equals -4, and there's going to be one at 1 right here. And so I can anticipate at least it's going to be broken into 3 pieces, this graph. I can tell from the numerator that the x-intercepts, actually there's just one, the x-intercept is x equals -1, so this is going to cross the x-axis right here at -1. And then now I have to see if there's a horizontal asymptote. So in order to tell that, I'm going to go ahead and compare the degree of the numerator and the degree of the denominator. And again, I'm going to go back and look at this table here. In that table, I could see in my function that the higher power was on the bottom. And so that's like this one right here. And it's saying if the degree of the denominator is greater than the degree of the numerator, then we have an asymptote at y equals 0, which is really the x-axis. So going back to look at that graph now, I can tell that we must have a horizontal asymptote at y equals 0, or the x-axis. So right in here, there's that horizontal asymptote, which is a little bit tricky because you do see that there's a point there on the x-axis, but that basically is just that one little hole that the graph was able to sneak through, but otherwise the graph is really going to just approach those asymptotes but never really cross them, other than that one little spot where it kind of like was able to find a little hole through. And so then the rest of the graph I'm going to take a look at from my calculator and see if I can get a good sketch of this. So let me go ahead and show you what that looks like on the calculator, but again, you probably want to put these in on your own and check for yourself. A standard window is best to use, and that's just do zoom 6, and that'll put you on a standard window. And this is what it's going to look like, and that makes sense with the framework I have set up. And so go ahead and sketch that. So I can see that in the middle there, this almost looks like a cubic graph that's like kind of reflected, and it's going to go ahead and cross that x-axis right there at -1. But then it's going to hug the asymptotes on either side. And then it almost looks like I have one of those hyperbolas in these opposite quadrants here, maybe one here, there, and then there's one over here on the other side. And although we don't have specific points on our graph out there other than the x-intercept, we could go ahead and get some of those from the table. But this is actually a pretty good representation based on what we have determined are the key characteristics of this graph. So again, look at the numerator to find x-intercepts. Look at the denominator for vertical asymptotes. If there is some sort of cancellation with the numerator and denominator, instead of being a vertical asymptote, and instead of being an x-intercept, that would actually just create a hole in the graph. And then compare the numerator and denominator's degree to determine, using that table, if there's a horizontal asymptote. But don't forget, if there's no horizontal asymptote, there could be a slant asymptote, and you can always refer back to example 3 to figure out how to determine where that might be. So our final examples are going to be about modeling with more complicated rational functions. And so when two real-world variable quantities are compared using a ratio or a rate, the comparison is a rational function. And you can solve problems about the ratio or rate by graphing the rational function. There also is a way in most of these to solve algebraically as well. And in this first example, I'll show you how to do that as well. So, but mainly we're going to, again, depend on the graphing calculator. So it says write a rational function to model the situation or use the given rational function. So in some cases they're going to give it to you, sometimes you got to write it. We're going to just skip this whole state the reasonable domain and range for the function, but we're just going to then use our graphing calculator to graph the function and answer the question. So a baseball team has won 32 games out of 56. So again, they're to start, they're 32 out of 56. And that's their record. And so that winning percentage is 0.571. So just taking how many games they've won out of how many games they played, 0.571. So how many consecutive games must the team win? So again, it's consecutive games. So if they keep playing and they keep winning, must the team win in order to change its percentage, raise its percentage to 0.60. So essentially what we're saying is we're going to add the same number of wins as we are going to add total games, because we want every new game that we play to be a win. And what that would look like then is to take that 32 over 56 and change it to 32 plus W and 56 plus W. So in other words, the number of wins that we add here are going to be actually the same as the number of games more that we play, because we're going to win every game. So it's consecutive games. And we want to know, when would this equal now 0.60? Now, algebraically, how we could solve something like that is, and probably even easier than graphing it, honestly, is we could put that 0.60 over 1, and then we could do the cross product. So we could take and we could multiply across the figure, you know how, or the equation. So if we multiplied across here, we'd get 32 plus W, and then if we multiplied across the other way, we'd be multiplying 0.6 by 56 and by W, and we'd get 33.6, and then the 0.6 times W would be plus 0.6 W. Now at that point, this is really easy to solve. All we have to do is get the variables on one side, the real numbers on the other. I'm going to go ahead and subtract 0.6 W, and I'm actually subtracting 0.6 W from really 1 W over here, and so that makes 0.4 W. And then when I subtract the 32 to the other side, that's going to leave me with 1.6. And if I were to then divide both sides by 0.4, I would get W equals 4. So that means that they would actually have to win and play 4 more games, so they have to win 4 more consecutive games in order to raise their winning percentage to 0.60. Now, I personally think that's really the best way to solve something like this, is to just solve it algebraically. But what you could also do, and when we're together in class I'll maybe show you this, but is we could take this left side of the equation, this 32 plus W over 56 plus W, and we could enter it into y sub 1 in our graphing calculator, and we could put the 0.60 into y sub 2, and we could graph those two things, and then we could see, using the trace calculate intersection function, where those two graphs cross. And then that would actually be at when W is 4. So that means 4 more games, 4 more wins, and our new winning percentage is 0.60. So again, I prefer really the algebraic way, because really it just involves doing the cross products. So maybe when you see those in the practice set, give those a try algebraically. Okay, so in our final example, 2 friends decide to spend an afternoon canoeing on a river. They travel 4 miles upstream and 6 miles downstream. In still water, they know that their average paddling speed is 5 miles per hour. If their canoe trip takes 4 hours, what is the average speed of the river's current? To answer the question, use the rational function. So in other words, that seems kind of complicated, but they did write this rational function for you, where the time relative to the current is equal to 4 over 5 minus c plus 6 over 5 plus c. And you can kind of tell where, if you look at the setup of this problem, where those things come from. One, because the average paddling speed is 5 miles per hour, and one is going against the current, one is going with the current. And then one is going 4 miles and 6 miles downstream. So then the one's getting the current against it, and the other is getting the current helping it, in other words, speeding it along. But anyway, if you take that function and you simplify it by adding those two together, and we're going to talk about that in our upcoming module about how we can actually add rational functions. We'll talk about getting common denominators and whatnot, but for now they just gave it to you in simplified version as 50 minus 2c all over 5 minus c times 5 plus c. And what we really want to know is, when does this equal 4? Because it was 4-hour trip. And so what we're going to try to do is figure out what is the average speed of the current, which is C. So again, this might be one that we could actually solve by algebra. We could do those cross products, but you could clearly see if you put 4 over 1 and you did the cross products, you'd be dealing with some sort of quadratic equation. And so instead, what we're going to do is we're going to go ahead and graph this. And like I said before, our strategy would be to put the rational function in for y sub 1. So again, be careful to make sure you have your entire numerator and your entire denominator parentheses. And then in y2, we can just simply put 4 in, which will be a horizontal line at 4. And when we graph this on the calculator, this is what it looks like. And you can see that that horizontal line in red is the line y equals 4. And the blue graph there is the graph of that rational function, which you can clearly see there's like horizontal asymptote, there's some vertical asymptotes and stuff in there. But what we really care about, most about, is where do the two graphs intersect each other. And I can see these actually intersect two different places. But remember that what I'm trying to find is the average current, and so the river's current. And so what we're trying to find should be something that's positive. So we're really going to target in on this one. And so these appear to cross when x is 4. And so C is it's actually pretty close to 4, but in fact, if I look in the table, or if I actually did the calculate function, so I'm going to go to second, and I'm going to go to calculate, and then I'm going to go to intersection, and then I'm going to choose the two graphs and select the graphs, and if I hit calculate or enter enough times, it's going to tell me that x is approximately 3.8. And that makes sense with what I'm seeing here, because you can tell that that is intersecting just shy of where x is 4. And if you were to put 3.8 back into that equation, and of course that's an approximation, but if you put 3.8 back in, it would approximately equal 4. So basically, at some point we will learn algebraically how to solve something like that, but for the meantime, we're just really going to depend on being able to use the graphing calculator and that calculate function, which is found under the trace menu when you hit the second key. And so, that it is a nice little application of rational functions. That does it for today's lesson. Thanks for coming to class.